Hello students, today we will explore chapter 9 hydrocarbons. So this is our theory part 16 and we will cover NCERT section 9.5.5 in it. So this is our disclaimer. Let us start by looking at what you will be able to do after this lecture. So our focus is on hydrocarbons, which are molecules made up of hydrogen and carbon atoms only. We will pay special attention to aromatic hydrocarbon today, a type of hydrocarbon with unique ring structure. Keep in mind, understanding their structure is key to predict how they behave physically and chemically. Now, what we are going to do? So, we are going to correlate the physical and chemical properties of aromatic hydrocarbons with their structure. This means we will explore how the arrangement of atom in this molecule affect things like boiling point, melting point, and how they react with other substances. Now, let us look at the specific names of the section that we are going to cover. So, we are going to see section 9.5.5, which focuses on properties of hydrocarbon. Then after, we will summarize the key points of the topics that we have learned in today's class. Now, starting with the physical properties of aromatic hydrocarbons. We will look at what makes this molecule unique, especially in terms of their polarity and solubility. As we go through each property, pay attention to how the structure of these molecules affect their behavior in different environments. Starting with the polarity, aromatic compounds are considered as non-polar molecules. This means that their overall charge distribution is balanced. So they don't have distinct positive or negative ends like water does. One reason for this non-polarity is the symmetrical distribution of electrons in the pi electron cloud system. In other words, the electrons are spread out evenly above and below the plane of the molecule, which keeps the charge balanced throughout. Next, small electronegativity difference is there between the carbon and hydrogen atom. So if I tell about the specific value, then hydrogen's electronegativity is 2.1 and carbon is 2.5. Since the difference is only of 0.4, it is not enough to create a significant dipole or separation of charge. This is why aromatic compounds don't mix well with the polar substances like water. So, on that basis, let us talk about solubility. Because aromatic compounds are non-polar in nature, they are insoluble in water, which is a polar solvent. This is a classic example of the rule like dissolves like. Non-polar substances don't mix with polar ones. Instead of aromatic hydrocarbons are immiscible with other non-polar or weakly polar organic solvents. That means they can dissolve in substances like benzene, ether or hexane, but not in water. This property is important in laboratory and industrial purposes where separation of substance is needed. To sum up, aromatic hydrocarbons are non-polar due to their symmetrical electron distribution and small electronegativity difference between carbon and hydrogen. As a result, they are insoluble in water but dissolve well in non-polar solvents. Continuing with the study of hydrocarbons' physical properties, next is physical state and appearance. This means whether they are solid, liquid or gas at room temperature and what they look like to the naked eye. Understanding this helps us identify them in real life. Notice that most simple aromatic hydrocarbons are colorless liquids at room temperature. For example, benzene is a common aromatic hydrocarbon and it is clear colorless liquid. This is different from some other hydrocarbon which might be gaseous or have color. As the molecular weight of aromatic hydrocarbon increases, they can become solid. For instance, naphthalene, which is heavier than benzene, is a white solid at room temperature. So, the bigger the molecule, the more likely is to be solid instead of liquid. Now, let's move on to another important property, their characteristic aroma. The word aromatic actually comes from the noticeable smell these compounds have. This property is a key reason why they are grouped together in the first place. So, the term aromatic was originally used because many of these compounds have pleasant or strong odors. For example, benzene and toluene both have distinctive smell. This is a historical naming, but it still helps us remember one of their main features. A key physical property of aromatic hydrocarbon is their distinctive smell. This means that even without seeing them, you might recognize them by their odor. It is a practical way to identify some of these substances in lab or in everyday life. For example, naphthalene balls, which are used in toilets and to protect clothes from moths, have a very unique smell. This is due to the aromatic hydrocarbon naphthalene. So their aroma is not just a scientific curiosity, it has real world uses. Let us pause here and recap. Aromatic hydrocarbons are often colorless liquids or solids, and their strong smells make them easy to recognize. Now, start by looking at the chemical properties of arenes, which are a type of hydrocarbon. Arene include compounds like benzene, and their chemical behavior is quite unique compared to other hydrocarbons. We will explore the main types of reaction they undergo, focusing on how their structure influence these reactions. So, arenes mainly undergo three types of reaction. It is important to remember that these reactions are different from those of alkanes and alkenes because of the special ability of benzene ring. Let us look at each type in detail. So, the first major type is called electrophilic substitution reactions. In this reaction, an atom or group attached to the benzene ring is replaced by another atom or group, usually because the ring attracts positively charged species called electrophiles. We will break down the main example of this reaction type further. The first example is nitration. In nitration, a nitro group, NO2, is introduced into the benzene ring, usually by reacting benzene and a mixture of concentrated nitric acid and sulfuric acid. This process is important in making explosives and dyes. Next is halogenation. Here, a halogen atom like chlorine or bromine replaces a hydrogen atom on the benzene ring. This reaction typically needs a catalyst such as iron in the third oxidation state with its chloride. Halogenated arenes are used in many industrial applications. Next, sulfonation is another key reaction. In this process, a sulfonic group SO3H is added to the benzene ring by reacting it with concentrated sulfuric acid or fuming sulfuric acid. Sulfonated arenes are important in making detergent and dyes. Friedel-Crafts alkylation. So, this is an process in which you add an alkyl group like a methyl or ethyl to the benzene ring. This reaction uses an alkyl halide and a catalyst such as aluminium chloride. It is widely used to make chemicals for plastics and fuels. Lastly, we have this Friedel-Crafts acylation. Now, this Friedel-Crafts acylation is similar to Friedel-Crafts alkylation in terms of their mechanism. But here we are introducing a acyl group which is COCH3, not a simple alkyl group. This reaction is also uses a catalyst and is important for making aromatic ketones which are used in perfumes and pharmaceuticals. The second main type of reaction is addition reaction. Unlike substitution, addition reaction breaks the aromatic ring structure, which is less common for arenes but can happen under certain conditions. Let us see some examples of those. First is hydrogenation of benzene. So it is an example of addition reaction. Here hydrogen gas is added to benzene under high pressure and temperature using a catalyst to form cyclohexane. This process is used for the production of nylon and other materials. Halogen addition is another example. In this reaction, halogen atoms are added directly to the benzene ring, breaking its aromaticity. This is less common and usually requires some special condition because it is important to know that it can happen. Lastly, we have the combustion, which is basically reaction with oxygen. Now, we are focusing on electrophilic substitution reaction first of all. Now, you will see one more name regarding this electrophilic substitution reaction, which is electrophilic aromatic substitution reaction, which is abbreviated as EAS in some places. Now, this is a key type of reaction in your hydrocarbon involving aromatic compound like benzene. Electrophilic substitution means that an atom, usually hydrogen in a molecule, is replaced by an electrophile. Let us see how this process works step by step. So, if you look at the overall reaction, this will give you a big picture view of what happens during the electrophilic substitution. Pay attention to which atom are being replaced and what new groups are introduced. So here you can see a diagram for the overall reaction. Notice how the incoming electrophile E plus is getting attached to the hydrocarbon and a hydrogen atom is being removed. This visual helps us to understand the changes happening at the molecular level. Now, let us break down the mechanism into its main steps. The first one is the generation of electrophile. Electrophile, you know that it is a particle that seeks electron often because it has a positive charge or a electron deficiency. In this step, the condition of the reaction creates the electrophile that will attack the hydrocarbon. The next step is the formation of carbocation intermediate. So whenever the electrophile attacks the hydrocarbon, it temporarily creates a positively charged intermediate called a hydrocarbon. This intermediate is less stable and is a key part of the reaction pathway. Third one is the removal of proton from the carbocation intermediate. This step restores the stability of the molecule by removing a hydrogen ion proton, resulting in the final substituted product. Notice how the molecule is returning to the neutral state in the last step. Now, if I draw the overall mechanism, then it looks like this. This diagram shows each step that we have discussed, including the movement of electron and the formation and removal of intermediate. Follow the arrows to see how the reaction proceeds from start to finish. The image illustrates the mechanism of electrophilic aromatic substitution EAS. In the first step, the slow step, an electrophile E plus attacks the electron-rich benzene, disrupting its aromaticity and forming a resonance-stabilized carbocation intermediate known as sigma complex or aranium complex. This complex shows delocalization of positive charge across the ring. In the second step, a base B minus deprotonates the carbon bearing the electrophile and a hydrogen, restoring the aromaticity of the ring and yielding the substituted product and the BH. This two-step process is characteristic of many aromatic functionalization reactions. Now, we will move on to further discussion of some specific examples. So, what was the general mechanism? As I said, first was the generation of electrophile. Now, here is a table showing different types of electrophile that your substitution reaction can use. And for instance, you can see in nitration the electrophile is NO2 plus, which while in halogenation it is Br plus, for sulfonation it is SO3. Then for Friedel-Crafts alkylation, the electrophile is R plus, meaning an alkyl cation. For Friedel-Crafts acylation, electrophile is an acyl cation, that means RCO plus. Each reaction has its own unique electrophile, and knowing this help us to predict the product. Notice how the structures of the electrophile changes depending on the reaction condition. The next step is formation of resonance stabilized carbocation. Here, the aromatic ring reacts with the electrophile to form a carbocation which is stabilized by the resonance. This means the positive charge can be spread out for several atoms, making the intermediate more stable. So, the carbocation intermediate is called as an aranium ion or sigma complex. Notice in the diagram how the positive charge is delocalized over the ring. This helps us to stabilize the intermediate even though the aromaticity is temporarily lost. So, why the aromaticity is lost? Because the carbon atom in the ring becomes sp3 hybridized. Normally, all carbon in benzene ring are sp2 hybridized for making the compound aromatic. The change to sp3 disrupts the structure and disrupts your delocalization as well, which is important for the aromaticity concept. Next, as a result of this, the aromaticity of the compound is lost and the system becomes less stable. Now what will happen? This molecule will exist for a very short time due to its less stability. Then how can it be stabilized? Basically, the H plus is removed from your given sigma complex to regain the aromaticity. Here is an example of that. What is happening? Your sigma complex is losing its H plus ion and the base, which is B minus, is acting as a proton abstractor and making the compound again an aromatic one. But this time here the H is replaced by the E, which is your electrophile. Now we can finally say that the aromaticity of the ring is restored and the compound is overall stable. Remember, the temporary loss and restoration of aromaticity is central to how this reaction works. So this was our general mechanism. Now we are continuing with this electrophilic substitution reaction, and we will focus on nitration, where a nitro group is introduced into the ring. Let's look at nitration in more detail. Nitration is the process where a nitro group written as NO2 is added to the aromatic ring. This is a classic example of an electrophile substitution reaction, and it is important in both chemistry and industry for making things like explosive and dyes. To carry out nitration, we use a mixture of concentrated nitric acid and concentrated sulfuric acid. This combination is called the nitrating mixture. The sulfuric acid acts as a catalyst and helps us to generate and regenerate the active species needed for the reaction. Got it? So what will be the mechanism? So the general mechanism will be followed. Now we have to see how it is specifically applied to produce the NO2 plus electrophile. What was the first step? It was generation of electrophile, and in this case it is generation of NO2 plus. So this ion is highly reactive and is what actually attacks the benzene ring. So what will be the equation for the generation of electrophile? HNO3 plus 2H2SO4 giving us NO2 plus H3O plus 2HSO4 minus. Now if you look at the reaction step, the first step is your sulfuric acid acting as an acid. Okay, and nitric acid is acting as a base here. Why? Because sulfuric acid is a stronger acid as compared to nitric acid. So this is the reason. Now remember, acidity and basicity is a relative concept, and it depends upon the relative interaction of both the species and not on the individual one. As a result of this, a strong acid such as nitric acid, here it is acting as a base. So what will it do? It will take H plus from the sulfuric acid and create a HSO4 minus anion. Next step is simply elimination of water. So your water will be eliminated from the protonated nitric acid to create the nitronium ion and water. Got it? Moving on further. What is the next step? The next step is formation of resonance stabilized carbocation intermediate or sigma complex. This intermediate is important because the positive charge can move around the ring, making the structure more stable. Notice in the diagram how the positive charge is delocalized across different carbon atoms in the ring. It helps explain why benzene can undergo substitution reaction without losing its overall stability. Here in this image, the electron-rich benzene acts as a nucleophile and attacks the electrophile nitronium ion, forming a sigma complex also known as arenium complex. The sigma complex is a carbocation that is resonance stabilized with the positive charge delocalized across the ring carbons as shown by the resonance structure. A base moves a proton from the carbon bearing the group and the hydrogen. The next step, restoring the aromaticity of the ring and yielding the nitrobenzene. So moving on to step 3, the next key event is the removal of proton from the carbocation intermediate. This step restores the aromaticity of the benzene ring, meaning the ring regains its stable delocalized electron structure. In the image, you can see how a base removes the hydrogen ion from the intermediate, which is a proton specifically, allowing the electrons to return to the ring. This completes the substitution and brings the benzene ring back to its original stable aromatic form. Now, what is the overall reaction? To sum it all up, this produces nitrobenzene from benzene. Remember, each step, formation of the intermediate and the removal of proton, all are essential for the reaction to proceed smoothly. Continuing the learning about this electrophilic substitution reactions, which are common for arenes like benzene. In this reaction, an electrophile replaces a hydrogen atom on the aromatic ring. Now we are focusing on halogenation, where a halogen atom is introduced into the ring using a Lewis acid as a catalyst. Here you can see the general reaction for the halogenation of your benzene. Notice how the benzene ring reacts with halogen like chlorine or bromine in the process of Lewis acid. This produces a haloarene, which is just a benzene ring with a halogen atom attached to it. Then after, if you look at the reagents involved, we use a halogen such as chlorine or bromine and a Lewis acid anhydrous FeCl3 or FeBr3 or AlCl3. The Lewis acid helps to generate a more reactive species from the halogen, making the reaction possible under mild condition. Now, let us focus on the electrophile in this reaction, how the electrophile is generated. The Lewis acid reacts with halogen atom to produce a halonium ion, such as Cl plus specifically in this case, where the Cl2 is reacting with FeCl3 to form Cl plus and FeCl4 minus. This Cl plus is the actual species that attacks the benzene ring. The diagram here shows the mechanism. So pay attention to how the electrophile is generated and how it interacts with the aromatic ring. Continuing about the halogenation reaction, here we see mono substitution. Here only one hydrogen atom on the benzene ring is replaced by a halogen atom such as chlorine or bromine. Here we have taken the example of chlorine, where your AlCl3 has generated what? It is generating a Cl plus. Now that Cl plus must have been reacted with the benzene to form this sigma complex, and further the AlCl4 minus is taking your chlorine from hydrogen from here. So AlCl4 is acting as a base and creating a chlorobenzene along with AlCl3 and HCl. Next, we can move on to polysubstitution. This means when more than one halogen atom is being substituting your hydrogen atom. The process depends on the number of electrophile which is present and the reaction condition. So excess substitution may lead to further substitution. Excess electrophile may lead to further substitution. Instead, more hydrogen are replaced, leading to further substitution. This is important in industrial processes where complete halogenation might be desired. With polysubstitution, multiple hydrogen atoms on the benzene ring are replaced by halogen atoms. This means the structure of the molecule changes more significantly and the properties of the compound can be very different from the original hydrocarbon. For example, if we use chlorine in excess with AlCl3 as a catalyst, we can replace several hydrogens on the benzene ring as shown in the diagram below. This is a classical example how 6 hydrogens are replaced and we are getting hexachlorobenzene, which is C6Cl6. Apart from this, we are getting 6 moles of hydrochloric acid. Again, what are we taking? We are taking excess of chlorine here. Remember, you must do this reaction in dark. Now, this reaction is in contrast with the halogenation of your alkyl groups, where I would say aliphatic groups, where we were using the UV light instead of dark. So they both are done in opposite conditions. Now we are looking at electrophilic substitution reactions, specifically sulfonation. So this is the type of reaction where sulfonic acid is introduced into an aromatic ring like benzene by replacing a hydrogen atom. Let us focus on how sulfonation process works and what is important in this organic chemistry. Here we see the sulfonation involves replacing a hydrogen atom on the aromatic ring with a sulfonic acidic group, which is written as SO3H. Notice the diagram showing the substitution reaction. This reaction is important because it introduces a functional group that can change the chemical properties of compound, making it useful for making dyes, detergents and drugs. To carry out sulfonation, we use reagents like fuming sulfuric acid or oleum. Fuming sulfuric acid is basically concentrated sulfuric acid with extra sulfur trioxide SO3 dissolved in it. This reagent provides the necessary condition for the reaction to take place efficiently. So, the key to this reaction is generating the electrophile, which is in this case SO3. An electrophile is a species that seeks out electron, and SO3 acts as a neutral electrophile. So, this is the only neutral electrophile that you will encounter in your class 12th standard, and it is this SO3 molecule that actually attacks the aromatic ring and replaces the hydrogen atom. So, what is the reaction? The equation shows here 2H2SO4 giving us SO3H, H3O plus and HSO4 minus explains how SO3 is produced from sulfuric acids. So, 2 molecules of sulfuric acid interact to generate 1 molecule of SO3 and a hydronium ion and a hydrogen sulfate SHSO4 minus. This step is crucial because it provides the SO3 needed for the sulfonation reaction. Now, continuing with the sulfonation reaction, our next part is to see how the formation of carbocation intermediate takes place, which is also known as sigma complex. This happens when the electrophile is attacked by the benzene ring, temporarily disrupting the stability. The positive charge is delocalized over the ring, which is important for the next step. Pay attention to how the structure changes in the diagram. Next, let's see how a proton is removed from the carbocation intermediate. So the HSO4 minus, which are produced in the first step of generation of electrophile, it acts as a base and removes a H plus from the sigma complex, restoring the aromaticity of the benzene ring and creating your sulfonic acid. So benzene sulfonic acid. Now, if you see here, then this has a negative charge on it, SO3 minus. This negative charge is satisfied by the H3O plus. So your benzene sulfonate, so basically it is not forming benzene sulfonic acid, it is only forming benzene sulfonate. In the last step, it is forming the benzene sulfonic acid, where the benzene sulfonate is taking a H plus from the H3O plus, by which it is creating a neutral species and water. Moving on further, next we will discuss the electrophilic substitution, which is Friedel-Crafts alkylation. In this process, a hydrogen atom on an aromatic ring like benzene is replaced by an alkyl group, which is just a chain of carbon and hydrogen atom. Remember, aromatic ring are stable structure found in many organic compound. Now let's see the reagents that are needed for this reaction. We use an alkyl halide, which is a compound where an alkyl group is attached to a halogen atom, like chlorine or bromine. This reaction also requires anhydrous aluminum chloride or AlCl3, which acts as a catalyst. Emphasize that anhydrous means without water, which is important for the reaction to work. Now let's talk about the electrophile in this reaction. The electrophile in this is the species that seeks out electron. And here it is a carbocation, which is a positively charged carbon atom. This carbocation is formed when the alkyl halide reacts with AlCl3. Notice how the reaction proceeds, where your AlCl3 is taking chlorine from CH3Cl, creating a carbocation, which is methyl carbocation specifically here, and AlCl4 is formed apart from it. Now next, what will happen? The arene such as benzene reacts with the alkyl halide in the presence of anhydrous AlCl3. This results in alkyl arenes, which means the aromatic ring now has an alkyl group attached to it. This is a classical example how we can modify hydrocarbon to create new compounds. So I have only focused upon the generation of electrophile here and not on the overall process. The overall process will remain same, and it will be basically the removal of hydrogen and introduction of this CH3 group. Apart from this, can also get some byproduct if the alkyl chain is longer. And there are some specific cases where the rearrangement of this carbocation is possible. So here it is not possible for case of methyl. This is the only possible carbocation. But there are many cases in which your generated electrophile undergoes rearrangement and then it reacts with the benzene ring due to the stability factor. So suppose there is a possibility that a primary carbocation is formed and it can be converted to the secondary carbocation by your rearrangement, then it will happen. Now this is a backlash for this Friedel-Crafts alkylation as well. Let's see how. So if you are taking ethyl benzene in case of your methyl benzene, so it can also be produced by taking your ethyl halide. Now we will talk about the limitations. As I said, it is seen that first of all, your alkylation is not a controlled one, because as soon as you introduce your alkyl group to the benzene ring, it activates the ring. We will talk about this activation later on. But due to this activation, your benzene ring is even now more electron rich, and hence it can undergo polyalkylation. This was not with the case of your halogenation, where your halogen introduction was deactivating the ring, but this alkyl group will activate your ring. So this can be your result. You can see here that the activated ring is undergoing your substitution reaction once more to create ortho and para derivative of di-substituted benzene ring. Now next, as I said, we can have the rearrangement of carbocation. How is it possible? Suppose we created a propene. What? Propane carbocation, not propene, a propane carbocation. Now what will happen? This propane carbocation can undergo 1,2 hydride shift. So basically the hydrogen from the carbocation carbon can move on to the middle carbon, the hydrogen from the middle carbon can move on to the positive charge of the carbon, creating a secondary carbocation. You can see it in the image that it is forming by rearrangement a secondary carbocation which is more stable. As a result of this, now this carbocation will react predominantly to produce isopropyl benzene. But okay, the propyl benzene will also be produced, but in a minor form. So basically, this is the formed product. Okay, this is the formed product, and it can rearrange to form this secondary carbocation. Now they both can react, and the major one will be coming from the isopropyl benzene and the minor one be from the propyl benzene, because the secondary carbocation is more stable. So you are getting a mixture of product rather than a single required product. So this is your second limitation. Now moving on further, the next is aryl halides and vinyl dihalides do not react. To generate electrophile AlCl3, would have to pull off the halide, making vinyl cation or aryl cation. Got it? So we have seen this part. So aryl and vinyl cation are extremely unstable. So this is very difficult to create a aryl or vinyl carbocation, because aryl or vinyl carbocation have a sp2 carbon with a positive charge, and sp2 carbon are electronegative as compared to the sp3, and electronegative element do not appreciate positive charge. As a result of this, they are difficult to form or unstable if they are formed. For example, if you are taking a vinyl halide, given in the example, if you react your FeBr3 with this, what will happen? Your Br will be removed and a vinyl cation will be formed. Now your vinyl carbocation is having a positive charge on sp2 carbon, which is an unstable one, because sp2 carbon is an electronegative one due to greater s character in the hybridized orbital. Similar to that, if you take aryl halide and try to react it with AlCl3, then it will form a phenyl carbocation, which is very unstable, and this is not formed also. It is formed to a very small extent or no. Therefore, these two are not possible to undergo this Friedel-Crafts alkylation. So this were the limitation. Now I would say to encounter this limitation, we have our next process, which is Friedel-Crafts acylation. So we are replacing a hydrogen atom by a acyl group, which is RCO, on the aromatic ring. How it will go? So for that, we will take acyl halide RCOCl and again react it with the anhydrous AlCl3. So here we are taking the same Lewis acid as we were taking in the case of Friedel-Crafts alkylation. Now, both of this, you can also take the acidic acid anhydride. Now, both of this can be used with the anhydrous AlCl3 to form the required electrophile. So this is your generation of electrophile. You can look here how your CH3COCl, which is being reacted with AlCl3, it removes the chlorine and forms the acylium ion. Now next, at what will happen? The arene react with the acyl halide or acidic anhydride in the presence of anhydrous AlCl3 to produce alkyl ketone. So this is your electrophile. The electrophile is being generated. Now what will happen? Your benzene, which is electron rich species, it will attack this electron deficient species to form the acetophenol. This is your overall process, and this is a ketonic group. Got it? Now what is the advantage of this process? First of all, your carbonyl group, which is formed in the end, is a deactivating group. We will see about this in the next upcoming lecture. Since it is deactivating, so it will not appreciate polysubstitution. Next part, we are not getting a carbocation which can rearrange. We are getting a acylium ion. So the problem of rearrangement is also being removed. So we will not get multiple product. We will get a single product. Now we will move on to the next reaction of benzene, which is addition reaction. First, let us look at hydrogenation of benzene. Hydrogenation means adding hydrogen atom to a molecule. In this case, we will see what happens when the benzene ring reacts with the hydrogen. Notice that the hydrogenation of benzene does not happen easily. It requires vigorous conditions, which means that we need high temperature and pressure. When benzene is hydrogenated, it forms cyclohexane, which is a saturated ring compound. This shows us that benzene is quite stable and does not react as easily as the other unsaturated hydrocarbons. Here you can see the chemical equation for this reaction. Benzene reacts with hydrogen gas to form cyclohexane. This is a good example of an addition reaction where hydrogen atoms are added to the benzene ring. Now, it is important to remember that this reaction needs high temperature and or high pressure to proceed. Without this conditions, benzene will not react with hydrogen. This highlights the stability of benzene ring and why special conditions are needed to break it. Finally, a nickel catalyst is also needed for this reaction. A catalyst is a substance that speeds up a chemical reaction without being used up itself. In this case, nickel helps the hydrogenation process happening more efficiently. So to sum up, hydrogenation of benzene to cyclohexane needs high temperature and or high pressure and a catalyst itself. Continuing the addition reaction, in this section we'll focus on how benzene, which is a common aromatic hydrocarbon, can undergo more types of addition reaction. So the specific example that we are going to see is your halogenation addition. Halogens are elements like chlorine or bromine that are very reactive. In this reaction, benzene reacts with halogen and we'll see that what product is formed. Pay attention to the conditions needed for this reaction. When benzene reacts with chlorine, it forms compound called benzene hexachloride. This compound is also known as gammaxane or BHC. It is important to remember these alternative names because they often appear in exams or textbooks. Here you can see the chemical equation for this reaction. Notice how the three chemical molecules are added to the benzene to form benzene hexachloride. And here we are using the light condition or the UV condition and not our dark condition, which was in the case of electrophilic aromatic substitution. So the reaction proceeds only under UV light, and UV light provides the energy needed for the reaction to take place. So without UV light, benzene and chlorine would not react in the same way. To summarize, three chlorine molecule which we write as 3Cl2 are added to the benzene molecule during this reaction. This is a good example of addition reaction where multiple atoms are added to a single molecule. Now we are going to discuss the last one, which is combustion reaction, which is a chemical process where a substance reacts with oxygen to produce heat and light. In the context of hydrocarbon, combustion is especially important because it is how fuels like petrol and diesel release energy. Let's look at how benzene, a common hydrocarbon, behave during combustion. Benzene burns with a sooty flame when heated in air. When benzene undergoes combustion, the main products are carbon dioxide, which is a gas and that we exhale, and water vapor. This is typical for hydrocarbon combustion. The carbon atom combines with oxygen to form carbon dioxide and the hydrogen atom forms water. Now, what is a balanced chemical equation? A balanced equation, as we know, contains the exact number of molecules involved on both sides, making sure mass is conserved. This helps us understand how reaction is proceeding and what amount is required for what amount of aromatic hydrocarbon. So if we take specifically C6H6, then it reacts with 15/2, I would say 15/2 moles of O2 to form 6 moles of carbon dioxide and 3 moles of water. Now, the general combustion for any hydrocarbon, we know for it is applicable to alkane, alkene, alkyne or any aromatic hydrocarbon is CXHY. So X and Y are the coefficient for carbon and hydrogen. They react with X plus Y by 4 moles of oxygen to form X moles of carbon dioxide and Y by 2 moles of water. Now to sum it up, what were the important points that we have gone through in today's lecture? First, about the physical properties. Aromatic compounds are non-polar in nature because carbon and hydrogen have a very low electronegativity difference. Next, due to this non-polarity, it is immiscible with a polar solvent such as water and miscible with other non-polar solvent or weakly polar organic solvents like your carbon tetrachloride. Next, about its physical appearance, it is a colorless liquid or solid. Then, in contrast with alkane and alkene that can be present in gaseous state, it can be only liquid or solid. Arenes undergo majorly 3 types of reaction. First is electrophilic substitution reaction. Second is addition reaction. Third is combustion reaction. Then moving on further. So if I talk about the electrophilic substitution reaction, we have electrophilic substitution reaction as nitration where NO2 plus was the electrophile. Then in halogenation, Cl plus was the electrophile. In sulfonation, SO3, which is a neutral electrophile. After that, we dealt with Friedel-Crafts alkylation, which is alkyl carbocation as electrophile. And lastly, we have this Friedel-Crafts acylation in which Rc plus O, which is acylium ion as the electrophile. This was the overall mechanism in which electrophile, which is a positively charged or neutral species that can accept electron, reacts with your electron-rich benzene to form a sigma complex or arenium complex, which is further stabilized by the resonance. Now, At last, a base can come and abstract the proton from this sigma complex, creating back your aromatic compound along with the substitution of hydrogen with a electrophile. Now next, we have some addition reactions as well. So we talked about hydrogenation of benzene, in which a benzene ring is directly converted to cyclohexane in presence of high temperature, or in some cases high pressure also. We require a nickel as a catalyst, and hydrogen is added to create a saturated compound, a completely saturated compound, which is cyclohexane. Then the next is halogenation addition, in which the benzene ring is being reacting with the 3 moles of Cl2 to produce hexachloride benzene. Got it? Here we are using the UV light in place of your dark condition, which was seen in the case of where? In the case of your electrophilic aromatic substitution. So this is also known as BHC, which is benzene hexachloride. Lastly, we talked about the combustion. The general equation for combustion was CXHY plus X plus Y by 4, giving us of oxygen, giving us X CO2 and Y by 2 H2O. So this was all for today's lecture. Thank you for joining the session. I hope this lesson was helpful.